Somewhere out there, statistically guaranteed if the universe is infinite, there is another you. Same atoms, same arrangement. Listening to another voice say these same words at this same moment. The distance to that other you, according to Max Tegmark's calculation, is 10 to the 10 to the 29th meters, a number so large that its written form would not fit inside the observable universe. And that is only one kind of multiverse physicists have proposed. There are others, built on completely different physics, so get comfortable and settle in. The universe has more in it than you thought. Part 1. The wrong question asked right. There is a question almost everyone asks the wrong way around. You have probably heard it phrased as something like, is the multiverse real? Are there parallel universes? Do alternate versions of us exist somewhere? These are reasonable questions, and they make for good headlines, but they share a hidden assumption that turns out to be wrong. They assume that the word multiverse refers to one specific thing, one well-defined picture, and that the only question left is whether that picture is true. Tonight, you and I are going to sit with a different question, a more honest one, and the answer is going to take us through some of the strangest territory physics has produced. The question is not whether the multiverse exists. The question is how many kinds of multiverse physicists have actually proposed, and whether any of them, or all of them, or none of them might be real at the same time. That difference matters more than it might sound. In casual usage, when someone says the word multiverse, they almost always mean the version from comic books and movies, parallel timelines, alternate yous. A world where you took the other job, married the other person, said the thing you wish you had said in the meeting last Tuesday. That picture is exactly one specific version of one specific multiverse proposal, and it is not even the version most professional physicists have in mind when they use the word. There are at least 4 logically distinct multiverse proposals in mainstream physics, and there are at least 9, if you count the more permissive census, some physicists prefer. And there are more if you include the speculative ideas at the edges of the field. None of them, by the way, requires anyone in a cape. All of them require thinking very carefully about what the word universe even means. Let me set the scene for what we are doing tonight. We are going to walk through, slowly and patiently, the entire layered architecture of multiverse ideas in contemporary physics. We are going to start with the version that requires almost no new physics at all, just the assumption that space keeps going. We are going to move into the version that comes out of cosmic inflation, the one where bubbles of new universes are constantly being born from an eternally expanding background. We are going to pass through the quantum mechanical version, the one where every measurement splits reality into parallel branches. We are going to reach the most radical version, the one where every consistent mathematics is itself a real universe somewhere. Then we are going to step outside the standard 4-level catalogue and look at cyclic models, brane collisions, holographic doubles, and simulations. And after all of that, we are going to ask the question physicists themselves are still arguing about, which is whether any of this counts as science at all. The names you will hear tonight are some of the most interesting in modern theoretical physics. Max Tegmark, who put the 4-level classification on the map, Alan Guth, and André Linde, who built the theory of inflation, Alex Vilenkin, who showed how inflation naturally becomes eternal, Hugh Everett, who in 1957 first proposed that the wave function never collapses, Leonard Susskind, who helped popularize the string theory family of solutions, Brian Greene, whose 9-fold census remains the most generous published count, Roger Penrose, whose conformal cyclic cosmology gives us a temporal multiverse instead of a spatial one, Paul Steinhardt, who helped invent inflation and now spends his time arguing against the multiverse it produces, Sabine Hossenfelder and George Ellis, who argue that most of this conversation is not physics at all. By the end of the video, every one of these voices will have had a turn at the question, why do physicists entertain these ideas to begin with? That is fair to ask. Most of us do not wander into a field expecting to populate it with infinite copies of ourselves. The honest answer is that the multiverse is not an idea anyone went looking for. It is an idea that keeps falling out of theories we already accept. Cosmic inflation, taken seriously, produces eternal inflation. Quantum mechanics, taken without the collapse postulate, produces many worlds. String theory, taken as a theory of everything, produces an enormous family of stable solutions. The cosmological constant problem, which we will look at in detail in a moment, gives us numbers so absurdly fine-tuned that the only mainstream explanation involves invoking other universes with other values. None of this was chosen for aesthetics. It is what falls out of the math when you stop adding patches. Here is the central thread I want you to hold throughout the next 2 hours. The word multiverse hides at least 4 logically independent ideas, each resting on different physics, each individually disputed, each producing a different answer to the question, how many? By the end of the video, the answer to that question is going to look very different from what you might have expected when we started. The most extraordinary possibility, when you actually count, might not be infinity. The most extraordinary possibility might be 1. Get comfortable. Settle in. We are going to be here for a while. The story we are walking through tonight is the story of how physics, by following its own equations as far as they will go, kept finding more and more universe behind the universe it started with. It is a story that has changed shape several times in the last 50 years, and it might change shape again before we are done. I want to be honest with you about the spirit of this video before we get into the details, because that spirit is going to colour every claim I make tonight. I am not going to try to sell you on any particular multiverse. I am not going to pretend that physics has settled the question of how many universes exist. It has not. What I am going to do is walk you carefully through what physicists have actually proposed, what the arguments for each proposal are, what the arguments against each proposal are, and where the entire program stands as of right now. By the end, you will be in a position to form your own opinion about which of the layered architectures we examine, if any, you find persuasive. The job tonight is not to convince you of anything. The job is to give you the maps. There is one more thing I want to mention, and it is about why this question matters at all. You might reasonably ask, why would anyone care how many universes are out there if we cannot ever visit them, communicate with them, or detect them? That is a fair question. The answer is that the multiverse, in its various forms, is not just an answer to a cosmological accounting problem, it is an answer to a much older question. The question is, why the universe is the way it is, why the laws of physics have the specific values they have, why the electron has the mass it has, why the cosmological constant has the value it has, why anything at all rather than nothing. For thousands of years, philosophers and theologians and scientists have asked these questions and produced different answers. The multiverse is the modern scientific contribution to that conversation. Even if no other universes can ever be observed, the idea of them shapes how we think about our own. For now, let us begin where every honest discussion of multiverses has to begin, which is not with the multiverse at all. It begins with the question of what we mean when we say one universe. Because if we cannot define one, we cannot count many. And as it turns out, the definition is harder than it sounds. Is less than break time equals 1s, is greater than number. Part 2. What counts as a universe anyway? Before we can count multiverses, we have to define what we mean by one universe. This sounds like a trivial preliminary, the kind of thing a physicist says only to get a definition out of the way before the real work starts. It is not. The way you define one universe determines the entire shape of the answer to how many. Different physicists, having quietly chosen different definitions, end up with wildly different counts, and most of the time, when two people are arguing about the multiverse, they are actually arguing about which definition to use. Sorting that out is the foundation for everything that comes next. So let us take our time with it. There are 3 working definitions of the word universe in modern physics, and each one produces a different multiverse. The first definition is the one most astronomers actually use. A universe, on this definition, is a causally connected region. Everything that has ever been able to send a signal to a given observer, or receive one, everything inside what cosmologists call your past light cone, or the slightly more generous notion of your Hubble volume, the sphere of space whose contents are still gravitationally relevant to you. By this definition, the universe is a real, finite thing. It is the part of space you and I share. It has a measurable size, roughly 46.5 billion light-years, in radius once you account for cosmic expansion, and it contains a definite, very large, but not infinite, number of galaxies. The second definition is the one a theoretical physicist might give. A universe, on this definition, is a region governed by a self-consistent set of physical laws. The same fundamental constants, the same particle masses, the same fine structure constant, the same cosmological constant. By this definition, 2 regions of space that happen to have different values for these constants are different universes, even if they sit beside each other in some larger arena. This is the definition that matters for the inflationary multiverse, which we will reach in the next act, because in that picture, different regions of the larger background really do end up with different physical constants. The third definition is the one a mathematician or a foundations of physics philosopher might give. A universe, on this definition, is a self-contained mathematical structure, a set of axioms, a set of objects, a set of relations among them, all internally consistent. By this definition, 2 universes are different if their underlying mathematics is different, regardless of whether anyone is inside them, regardless of whether they bear any resemblance to ours. This is the most permissive definition, and it is the one that powers Tegmark's 4th level, which we will reach near the end of the second act. Notice what happens when you apply each of these definitions to the question how many. If a universe is a Hubble volume, then the count depends on how much space exists beyond ours. If the total space is finite, the count is some finite number, possibly small. If the total space is infinite, the count is infinite, because you can tile infinite space with Hubble volume spheres. If a universe is a region with its own physical laws, then the count depends on how many different sets of laws are physically realizable. The string theory program suggests an enormous number, somewhere around 10 to the 500th, as a famous early estimate, with more recent work pushing the count much higher. If a universe is a mathematical structure, then the count is every consistent mathematics, which is itself an infinite collection of infinities. You can see why physicists keep talking past each other on this topic. 2 people who agree completely about the physics can disagree wildly about the multiverse, simply because they are silently using different definitions of universe. One says yes, there are infinite universes, meaning Hubble volumes. The other says no, those are all just our universe extended outward. Neither is wrong. They are answering different questions. Part of what we are doing tonight is being careful to keep these definitions distinct, so that when we ask how many, we know which kind of how many we are asking about. There is a piece of vocabulary we are going to use as the spine of the next act, and it is worth introducing now. Max Tegmark, a cosmologist at MIT, published an influential paper in 2003 classifying multiverse proposals into 4 levels. Level 1 is the multiverse of Hubble volumes inside a larger, possibly infinite space. Level 2 is the multiverse of inflationary bubbles, each with its own physical constants. Level 3 is the multiverse of quantum mechanical branchings. Level 4 is the multiverse of mathematical structures. The levels are roughly ordered by how radical the assumptions are. Level 1 requires almost nothing new. Level 4 requires everything to be reconsidered. The 4-level scheme is not the only published taxonomy. Brian Greene, in his 2011 book, The Hidden Reality, listed 9. There is the quilted multiverse, which is essentially Tegmark's level 1. There is the inflationary multiverse, which is level 2. There is the quantum multiverse, level 3. There is the ultimate multiverse, level 4. Greene added the brain multiverse, in which our universe is one membrane in a higher dimensional bulk and other membranes float alongside. He added the cyclic multiverse, in which time itself is multiplied rather than space. He added the family of string theory solutions as a separate category. He added the holographic multiverse, in which the bulk and the boundary are two descriptions of one physics. He added the simulated multiverse, in which our universe is one program among many running on some larger substrate. I am bringing this up now, before we even start walking through the levels in detail, because I want you to understand that the question how many multiverses are out there is genuinely ambiguous. The answer depends on which physicist you ask, which taxonomy they use, which definition of universe they have silently chosen, and which proposals they take seriously. Part of the honest work tonight is going to be noticing where these ambiguities live, rather than pretending they are not there. Notice as well how each of these definitions reaches in a different direction. The Hubble volume definition asks about geometry. The physical laws definition asks about ontology. What kinds of distinct rule sets can be instantiated by reality? The mathematical structure definition asks about logic. What kinds of internally consistent systems can be said to exist at all? A physicist working in observational cosmology will tend toward the first. A physicist working on inflation or string theory will tend toward the second. A theoretical physicist with philosophical inclinations will tend toward the third. None of them is being unreasonable. They are each picking the definition that does the most work in their own research, and the result is that they end up with completely different numbers when they ask the same English language question. This is the kind of confusion that most popular discussions of the multiverse never address. You will read an article claiming that physicists have proven a multiverse exists, and the article will quote one physicist using one definition. The next article will say, physicists have not proven anything of the sort, and it will quote a different physicist using a different definition. Both can be technically correct, even though they appear to contradict each other. Most of the noise in the public conversation about the multiverse comes from this kind of mismatched definitions crosstalk. We are going to avoid it tonight by being explicit at every step about which definition we are using. There is one more thing I want to mention before we move on, because it is going to set up the next part. Of all the reasons physicists have for taking the multiverse seriously, one stands above the rest. It is not philosophical. It is not aesthetic. It is a single number, a measured value that, according to our best calculations, should be enormously larger than it actually is. The discrepancy between what physics predicts and what we observe is so large that there is essentially no precedent for it in the history of science. That number is what pushes the multiverse from being an idea physicists humor to being an idea physicists feel compelled to take seriously, and we cannot understand the rest of the story without understanding it. Let me show it to you. Is less than break time equals 1s is greater than number part 3, the cosmological constant problem. The number I want to introduce you to is called the cosmological constant, and the story of it is, in a quiet way, the most embarrassing story in modern physics. It is also the single strongest reason that any of the multiverse proposals we are walking through tonight get serious airtime in mainstream cosmology. So even though this part is going to feel like a brief sidestep from the count itself, I want to be careful with it, because everything else we discuss is going to refer back to this one number. Here is what the cosmological constant is, in plain terms. Empty space, according to quantum field theory, is not really empty. It is filled with what physicists call vacuum energy, a kind of background energy density that exists even when no matter or radiation is present. This energy density, if it exists, would have a gravitational effect. It would push space apart, accelerating the expansion of the universe at large scales. For most of the 20th century, cosmologists assumed this vacuum energy was zero because no one had measured any acceleration. Then, in 1998, observations of distant supernovae showed that the expansion of the universe is in fact accelerating, exactly as a small positive cosmological constant would predict. The acceleration is real. The cosmological constant is real. It is small, but it is not zero. Its measured value, expressed in the natural units physicists prefer, is about 10 to the minus 122nd. Now, here is the embarrassing part. If you take quantum field theory and ask it to calculate the value of the vacuum energy from first principles, the answer it gives is roughly 1. Not 10 to the minus 122nd. 1. The discrepancy between the calculated value and the measured value is 120 orders of magnitude. That is 10 followed by 120 zeros. The measured cosmological constant is smaller than the calculated one by a factor of a googol, multiplied by another googol, with 20 more zeros tacked on. This is not a small error. It is, by a very large margin, the worst quantitative prediction in the history of science. It is so bad that physicists have a name for it. They call it the cosmological constant problem. Take a moment with that. In most areas of physics, when a calculation disagrees with observation by a factor of 2, we worry. By a factor of 10, we panic. By a factor of 100, we conclude something is fundamentally broken in our theory. By a factor of 10 to the 120th, we are not in a regime where the usual diagnostic instincts even apply. Something is going on, and it is not a small correction. It is a structural feature of how the universe works that our theories do not currently capture. There are, in principle, a few possible kinds of solution. One is that the calculation is wrong, that some new physics we have not yet found cancels the predicted vacuum energy almost exactly, leaving only the tiny residual we observe. This is mathematically possible, but it requires a cancellation accurate to 1 part in 10 to the 122nd, which is not something nature has any obvious reason to provide. Another is that the measured value is somehow wrong, that what we are seeing is not really vacuum energy at all, but some other effect masquerading as it. Decades of follow-up observations have not supported this. A third possibility is that the constant simply has the value it has, with no explanation. Physics has historically resisted this kind of brute fact answer on the grounds that explaining things is what physics is for. And then there is the fourth possibility, the one that brings the multiverse into the picture. The multiverse explanation goes like this. Suppose the cosmological constant is not a fixed fundamental quantity, but a variable that can take different values in different universes. Suppose further that universes exist with every possible value, from large positive to large negative, spread out across some enormous family of distinct universes. Then in most of them, the value is large, and large values prevent galaxies from forming. Either the universe expands so fast that matter never clumps together, or it recollapses so quickly that there is no time for anything interesting to happen. In a tiny fraction of universes, the value happens to be small. In that tiny fraction, galaxies form, stars burn, planets cool, and observers eventually emerge to wonder about their cosmological constant. Those observers, when they measure their constant, find a small value because they could not exist anywhere else. This is called the anthropic explanation, and it has a famous history. In 1987, the physicist Steven Weinberg used exactly this reasoning to predict a small positive cosmological constant a decade before it was measured. He argued that if the multiverse picture is correct, the most probable value an observer would measure is the largest one compatible with galaxy formation, which is roughly the value we now measure. When the actual measurement came in, it sat right where Weinberg had predicted. This is not proof, but it is a successful prediction made on the basis of multiverse reasoning that turned out to fit the data. Many physicists found this very persuasive. It is also important to understand why other physicists found this very unpersuasive. The anthropic explanation does not actually predict any single value. It only says that the value we measure must be small enough to permit our existence. It does not predict whether the value should be exactly what we see, or smaller, or slightly larger. It does not specify what other constants should look like. As an explanatory framework, it has the property that it cannot really be wrong, which, depending on your taste in scientific arguments, is either its strength or its fatal weakness. We will come back to this objection in detail later. For now, just notice the structure. The cosmological constant problem is real. The anthropic multiverse explanation is the one most cited solution in mainstream cosmology. It is not the only solution, but it is the one that keeps the multiverse idea respectable. What this means for our central question is that the multiverse, in some form, is not a hobby of fringe physicists. It is the most cited explanation for the largest unsolved quantitative puzzle in modern physics. If you want to dismiss the multiverse, you have to do something with the cosmological constant problem first, and there is no agreed-upon replacement explanation that works as well. This is the pressure that pushes physicists into taking seriously all four of Tegmark's levels, even the ones that look philosophically uncomfortable. It is not because they want to. It is because the number on the left side of the equation is 10 to the minus 122nd, and the number on the right side, before the multiverse argument, is 1. It is worth pausing on the scale of that discrepancy one more time before we move on, because numbers this enormous become abstract very quickly. Imagine that you weighed a single grain of sand on a kitchen scale. Now imagine that the scale reported the weight as more than the combined mass of every star, planet, and galaxy in the observable universe. That ratio is roughly 10 to the 80th. The cosmological constant discrepancy is 40 more orders of magnitude beyond that. It is not just wrong, it is wrong in a way that has no analogue in any other measurement in the history of physics. When you grasp how extreme the disagreement is, the willingness of serious physicists to entertain serious-sounding multiverse proposals starts to look less like overreach and more like an honest response to the size of the problem. Of those four levels, the first is so simple that some physicists do not even consider it a multiverse at all. It requires no new physics. It requires only that space, the same space we are in right now, keep going beyond what we can see. If it does, then by an argument that is almost embarrassingly direct, there are not just other universes out there. There are infinitely many. And in those infinitely many, somewhere, statistically guaranteed, is another you. Let me show you the math. Is less than break time equals 1s. Is greater than number, part 4, level 1, the universe beyond the horizon. The first multiverse we are going to walk through is the gentlest one. It requires no new fields, no new particles, no quantum branching, no exotic mathematics. It requires only that the space we live in extends beyond the part we can see. If it does, then by the most modest argument anyone has ever made about cosmology, there are not only other universes out there, there are infinitely many, and inside them, statistically inevitable, are infinite copies of you. This is what Max Tegmark calls the level 1 multiverse, and it is the one that almost nobody calls a multiverse, because it sounds like just more universe. Let us start with what we actually see. The observable universe is a sphere centered on you, the observer. Its radius is set by how far light has been able to travel since the Big Bang roughly 13.8 billion years ago. Because space has been expanding the whole time, the matter that emitted the most distant light we can now detect is currently about 46.5 billion light-years away. So when we say the observable universe is 46.5 billion light-years in radius, we mean the sphere, whose surface is made of the most distant matter whose light has had time to reach us. Inside that sphere, there are roughly 2 trillion galaxies. Outside it, we cannot directly see anything. Light from those regions has not had time to arrive. By the rules of relativity, no information at all can have travelled here from beyond the cosmic horizon. The question is what lies beyond. The honest answer is, we do not know. We have measurements that constrain it. The cosmic microwave background, the leftover light from when the universe became transparent about 380,000 years after the Big Bang, has a temperature that is uniform across the sky to within about 1 part in 100,000. The geometry of space, measured from the angular size of fluctuations in that background, is flat to within about 1/4%. If the universe is flat and the same physics holds everywhere, then the simplest assumption is that it just keeps going. A flat, infinite space is one of the simplest mathematical objects there is. It would be strange to assume our particular slice is the only part that exists. If you take that assumption seriously, and you assume that the universe extends infinitely in all directions with roughly the same physics, then something remarkable follows. The total amount of universe is unbounded. The number of Hubble volumes, tiling that infinite space, is also unbounded. Inside each Hubble volume, the number of possible arrangements of matter is enormous but finite. There are only so many atoms in a Hubble volume, only so many possible positions and momenta for each one, only so many distinguishable configurations. Even allowing for quantum effects, the number of distinct possible configurations of a Hubble volume is finite. Very, very large, but finite. This sets up a pigeonhole argument. You have an infinite number of Hubble volumes. Inside each one, only a finite number of possible configurations. By the same logic that guarantees if you put infinitely many letters into finitely many mailboxes, some mailbox will receive infinitely many letters, you can guarantee that some configurations will recur. Not just similar configurations, exactly identical ones. If the number of Hubble volumes is genuinely infinite, every possible configuration must occur, and must occur infinitely many times. There is no statistical wiggle room. It is a pure pigeonhole result. Tegmark calculated what this means for ordinary observers like us. The number of possible Hubble volume configurations that include an exact copy of you doing exactly what you are doing right now is a finite fraction of all possible Hubble volume configurations. So by the pigeonhole argument, there must be infinitely many Hubble volumes that contain exact copies of you. He went further and calculated, on average, how far apart these copies are likely to be. The answer is a number called 10 to the 10 to the 29th meters. Take a moment with that. The exponent of an exponent. 10 to the 29th is itself a number with 30 digits. 10 to the 10 to the 29th has 10 to the 29th digits when you write it out. The written form of the number would not fit inside the observable universe, no matter how small you wrote the digits. He also calculated the distance to an exact copy of the entire observable universe, with you and everyone else in it doing exactly what we are doing here, including this video playing on a screen somewhere. That distance on average is about 10 to the 10 to the 115th meters. These are not poetic numbers. They are the unavoidable consequence of assuming infinite space plus a finite number of possible configurations per Hubble volume. The argument is, in some ways, the most modest in all of cosmology. It requires no new physics, only an assumption about the size of space. The natural reaction to this is to ask whether the assumption is really safe. Is space really infinite? The honest answer is, we cannot prove it. What we can do is establish lower bounds. From the curvature measurements of the cosmic microwave background, we can say with high confidence that the universe is at least 250 times larger than the observable part. That puts a lower bound on the total size of something like 23 trillion light-years across. That is a minimum. It could be much larger. It could be unbounded. The data are consistent with either. If the universe is finite but very large, then level 1 as a true multiverse evaporates. You get only a finite number of Hubble volumes, possibly without any exact copies of you. If the universe is truly infinite, then level 1 is the most modest infinity in physics. The argument turns entirely on the question of whether space, the ordinary space of general relativity, continues beyond what we can observe. There is something philosophically heavy about level 1 that I want to sit with for a moment, because it does not get talked about much. Level 1 does not invoke quantum branching, or alternate physical constants, or any new fields. It just says, if space keeps going, and there are only so many ways to arrange matter, then you must repeat. Somewhere out there, statistically inevitable, is another you. Same atoms, same arrangement, same thoughts, listening to another voice say these same words at this same moment. Another you in a slightly different version of the room who heard the doorbell ring just then. Another you in a different version still, who is currently asleep. Another whose life diverged in some small way decades ago. Another whose life diverged in some enormous way decades ago. Every variation that could ever exist, statistically guaranteed somewhere in the immense reach of an infinite space. For some people, this is comforting. For some, it is unbearable. Every loved one ever lost is alive somewhere. Every regret of yours has been corrected somewhere. Every disaster that befell you was avoided somewhere. Every disaster you avoided also happened somewhere. The space is so large that everything possible has happened, and everything possible is happening right now. The catch is that you cannot reach any of it. The other Hubble volumes are, by definition, outside our cosmic event horizon. Light cannot travel to them. They cannot signal to us. Whatever exists out there is, for all practical purposes, in a separate reality. Level 1 is not parallel worlds you can visit. It is more universe like ours, beyond a horizon we cannot cross. Some physicists consider this trivial. It is, after all, just more universe, with the same physics, behaving the same way. There is no surprise in it. There is no new mechanism. It is what you get if you assume the obvious thing about an infinite space. Other physicists consider it one of the strangest implications in all of cosmology because it dissolves something we usually take for granted. It dissolves uniqueness. The you sitting in your room tonight is, on this picture, one of an infinite number of yous. Your individual life is one instantiation of a pattern that occurs infinitely, often across an infinite space. Whether that is trivial or shattering depends, I think, on how you feel about your own particularity. There is one more thought about level 1 I want to offer before we move on, because it puts the doppelganger calculation into a perspective most popular treatments skip. The pigeonhole argument that produces other copies of you does not actually require quite as many assumptions as it might first appear. It requires only that physics has a finite information density at the quantum scale. that the matter configurations of a Hubble volume can be specified by a finite, if enormous, set of quantum numbers, and that those configurations recur if you sample enough volumes. All three are accepted by mainstream physics. The Bekenstein bound, derived from black hole thermodynamics, places a strict upper limit on the amount of information any finite region of space can contain. For a region the size of our observable universe, that bound works out to something like 10 to the 123rd bits. Enormous, but finite. The configurations are therefore countable. And in infinite space, countable configurations have to repeat. The argument is, in this sense, almost rigorous. It is the conclusion of standard physics combined with a single assumption about the size of space. The discomfort, if you have any, comes from realizing how strange that assumption actually is. We are used to thinking about infinity as a mathematician's tool, something useful for limits and calculus, not as a literal feature of the world. But if the universe is genuinely infinite, then mathematical infinity is also physical infinity, and the consequences ripple outward in ways that are difficult to fully absorb. Every story that could be told somewhere is being told. Every life that could be lived somewhere is being lived. Every possible variation of human experience, however unlikely it sounds, is somewhere actual. The universe, on this picture, is not a place where unusual things sometimes happen. It is a place where every unusual thing happens, and where the ordinary things happen infinitely often. The mathematician Hermann Weyl once said that mathematics is a kind of dream, structured by axioms and explored by proof. Level 1 tells us that the dream is also the world. If the universe is infinite, then the infinity that mathematics has always treated as a useful idealization turns out to be the literal truth about how much there is. Level 1 is the flaw of the multiverse architecture. It is what you get from assuming the most uncontroversial possible thing about cosmology. To get the next level, you have to assume something more, and what you have to assume is that the laws of physics themselves can vary from region to region. That is a much bigger step, but it is also the level that has the most direct connection to the cosmological constant problem we discussed in the last part. Let me show you how. Is less than break time equals 1s is greater than number. Part 5. Level 2. Inflationary bubbles. Level 1 assumed the same physics everywhere. Level 2 takes the more radical step. It asks what happens if the laws themselves can change from region to region, if the values of the physical constants we treat as fundamental are actually local features of our patch, frozen in long ago when our piece of the universe was forming. The mechanism that makes this picture coherent is called cosmic inflation, and it is one of the most successful and one of the most contested ideas in modern cosmology. Tonight, I want to walk through it slowly, because the inflationary multiverse is what most professional cosmologists actually mean when they use the word multiverse, and the picture is not quite what most people imagine. Inflation is, in its standard form, a brief period of extremely rapid expansion in the first instant of the universe. The numbers are almost not numbers anymore. In a span of about 10 to the minus 36th of a second, a tiny region of space expanded by a factor of about 10 to the 26th. To get a sense of that ratio, imagine taking something the size of a proton and expanding it to the size of an oak tree in a small fraction of a second. The geometric stretching was so violent that it ironed out any pre-existing curvature, any pre-existing inhomogeneity, any pre-existing structure. What was left, when inflation ended, was a hot, dense, almost perfectly smooth, and almost perfectly flat universe, which then cooled and expanded more sedately into what we now see. The reason cosmologists believe this happened is that it neatly explains several otherwise puzzling features of our universe. The flatness, the uniformity of the cosmic microwave background across regions that should never have been in causal contact. The small but non-zero density fluctuations that seeded the formation of galaxies. These features are predicted by inflation and otherwise hard to explain. The basic inflationary picture is now part of mainstream cosmology, having been proposed by Alan Guth in 1980 and refined by André Linde, Andreas Albrecht, Paul Steinhardt, and others through the 1980s. Now, here is the move that takes us from inflation to the level 2 multiverse. Once you have a theory of inflation, you can ask what happens at the boundary between the inflating phase and the post-inflationary phase. In Linde's chaotic inflation model from 1983, and in Alex Vilenkin's analysis a few years later, the result was unexpected. In most reasonable inflationary models, inflation does not end everywhere at the same time. It ends in some regions, while continuing in others. The regions where it ends become pocket universes. The regions where it continues stay in the inflating phase, expanding faster than any signal can cross them, until at some point, in some subregion, they too undergo a transition and end inflation locally, becoming a new pocket. The process never stops globally. It just keeps producing new pockets forever. This is called eternal inflation, and once you have it, you have the level 2 multiverse for free. Each pocket universe is a separate piece of post-inflationary reality. Each one had its own moment when inflation ended, which means its own moment when the values of the physical constants got set. And here is the key point. In many inflationary models, the values that get set during the end of inflation are not the same from pocket to pocket. The dynamics of the inflationary field can settle into different stable configurations in different pockets, which means different values for things like the strength of the strong nuclear force, the mass of the electron, the cosmological constant. The picture to hold in your mind is this. Imagine an enormous, eternally expanding background, faster than light in its local stretching, never finishing, going on forever. Inside that background, bubbles of new universes nucleate. Each bubble represents a region where inflation locally ended and ordinary expansion began. Each bubble has its own physics. Most bubbles are sterile, with constants set to values that prevent atoms from being stable, or prevent galaxies from forming, or do not allow chemistry of any kind to develop. A small fraction of bubbles happen to have constants in the narrow window that permits complex structure. We live in one of those rare bubbles. This is where the cosmological constant problem comes back into the story. In the level 2 multiverse, the cosmological constant is not a fundamental fixed number. It is a parameter that gets set by local physics during the end of inflation, and it gets set differently in different bubbles. Across the entire collection of bubbles, the cosmological constant takes every possible value. In most, the value is too large for galaxies to form. In a tiny fraction, the value is small enough for structure to develop. Observers can only arise in that tiny fraction, and so observers, when they measure their cosmological constant, find a small value. The level 2 multiverse is the cleanest physical realization of the anthropic argument we discussed in part 3. There is one more piece of theoretical machinery that needs to be brought in here, because it is what gives the level 2 multiverse its specific numerical content. That machinery is string theory. String theory is, in its modern form, a candidate for a unified theory of all the fundamental forces, including gravity. It does this by replacing point particles with tiny vibrating strings, and by requiring that space-time have more dimensions than the 4 we observe. The extra dimensions, if they exist, must be curled up so small that we do not notice them, and the geometry of how they are curled up determines the effective physics in the 4 large dimensions we live in. The number of distinct ways to curl up the extra dimensions, consistent with all the constraints of the theory, is enormous. The famous early estimate from work in the early 2000s by Busso, Polchinski, Susskind, and others was about 10 to the 500th. Each of those configurations corresponds to a distinct possible set of physical constants. Each is a different metastable vacuum of string theory, with its own version of low-energy physics. More recent work by Washington Taylor and collaborators in 2015, looking at F-theory flux compactifications, raised the estimate to roughly 10 to the 272,000th. Whatever the exact number, it is large enough to populate the requirements of the anthropic argument with room to spare. Eternal inflation, populated by string theory's enormous family of vacua, is the standard professional version of the level 2 multiverse. I should mention an important countercurrent here. In recent years, work by Kumran Vafa and his collaborators on what they call the swampland conjectures has argued that most of the apparent string theory vacua may not correspond to consistent quantum theories of gravity. If their conjectures hold up, the effective number of allowed vacua could be much smaller than the original estimate, possibly even zero. This is an active area of research, and the outcome would significantly change the picture. For now, the Level 2 multiverse remains the working framework for most cosmologists who take the multiverse seriously, but its specific size is genuinely uncertain. There is also one tantalizing piece of potentially observational evidence I want to mention, with appropriate skepticism. In 2004, a region of the cosmic microwave background was identified that is about 70 microkelvin colder than the surrounding sky. It is located near the constellation Eridanus, and it is roughly 1.8 billion light-years across. It is called the Cosmic Microwave Background Cold Spot, and it is colder than statistical fluctuations alone would predict, though not by a dramatic amount. The leading explanation is mundane, that there is an unusually large region of low matter density between us and that part of the sky, which causes light passing through it to lose a tiny amount of energy. But a more speculative explanation has been on the table for some time. It is that the cold spot is the imprint of a collision between our bubble universe and a neighbouring one during the inflationary epoch. The predicted signature of such a collision, worked out by Matthew Kleben, Anthony Aguirre, and others, is a disk-like region of slightly different temperature with a distinctive polarization pattern. The cold spot does not have all the predicted features, but it has some, and it has not been definitively explained by the foreground void hypothesis either. Searches continue. If the bubble collision explanation ever turned out to be right, it would be the first direct observational evidence of another universe. So far, that is a big if. The reason I want you to hold the level 2 picture clearly is that this is the version most professional cosmologists actually have in mind when they say multiverse. It is not parallel timelines. It is not alternate U's in the next room. It is an immense sea of pocket universes, born from an eternally inflating background, each with its own physics, most of them sterile, and a tiny fraction containing complexity. Our universe is one such pocket. It has the physics that happens to allow us to exist. There are, on this picture, an unbounded number of other pockets we cannot reach, each with its own version of the laws. This is the picture that Paul Steinhardt, who helped invent inflation, has come to reject most strongly. He argues that eternal inflation, taken seriously, predicts that every possible value of every possible constant will be realized somewhere. Therefore, it predicts no specific value for any constant. Therefore, it has no real predictive content. Therefore, it has stopped being science. We will come back to his argument in detail later. For now, just note that the Level 2 multiverse is the version most under serious philosophical attack from inside physics itself. Let me sit with the picture for one more minute before we move on, because there is something about Level 2 that gets lost in the technicalities. If Level 2 is right, then most of the universes that exist are not anything like ours. Most of them have constants set to values where atoms cannot hold together, where the electron is too heavy for chemistry, where the strong nuclear force is too weak to bind quarks into protons, where the cosmological constant is so large that no structure ever forms. Most of them are empty in a very specific way. They have space, they have time, they have something resembling physics, but they have nothing in them more interesting than a featureless drift of fundamental particles never quite finding each other. Picture it for a moment. An enormous, ongoing, ceaseless inflation in the background, faster than light at every point, producing pocket after pocket like foam at the edge of a wave. Each pocket settles into its own physics. Most of them never see a star. Most of them never see a stable atom. They expand, they cool, and nothing happens. There are no observers. There is no one to notice that the universe is empty. The pocket simply exists, governed by its own laws, indifferent to its own sterility. In the rare pockets where the numbers happen to allow complexity, observers eventually arise. They look at their own laws, find them improbably fine-tuned, and wonder why. The level 2 answer is that the laws are not really fine-tuned. They are randomly distributed, and we live in one of the rare pockets where the random sample happened to be habitable. The improbability of our particular constants is exactly compensated by the enormity of the family of pockets in which our constants are not realized. This is the multiverse doing the work the anthropic principle requires it to do. Whether or not you find the explanation persuasive, it is the cleanest physical realization of the idea that has ever been proposed. One more detail before we go. The bubbles, in the standard picture, are not floating in pre-existing space. Each bubble carries its own space with it. The bubble walls are not located somewhere in a larger geometry. They are the boundary between regions that have ended inflation and regions that have not. Two bubbles, from inside, look infinite. They each have infinite Hubble volumes within them. The level 2 multiverse, in other words, is not a collection of finite pocket universes scattered through a larger arena. It is a collection of internally infinite universes, each one containing its own level 1 structure, all of them embedded in an even larger inflating background. The infinities are stacked. If level 1 is the multiverse you get by extending space, and level 2 is the multiverse you get by extending the rules of physics across space, then there is a third level that does something neither of the first two does. It does not extend physical space at all. It extends something stranger. It extends the wave function of quantum mechanics. The result is a multiverse that is not located out there somewhere. It is, in a sense, layered over our own world, every moment, every measurement. Let me try to walk you through what that means. Is less than break time equals 1s. Is greater than number, part 6, level 3, the quantum branches. The first two multiverses we have explored both live in physical space. Level 1 is more space behind the cosmic horizon. Level 2 is bubbles of different physics in a larger, inflating background. In both cases, the other universes are far away. They are out there somewhere, beyond our reach, but they are physically located in some place. Level 3 is different. Level 3 does not live in physical space at all. It lives inside the mathematics of quantum mechanics, in a structure called the universal wave function. To explain what that means, I need to take you back to the foundations of quantum theory, to the most famous and most misunderstood experiment in modern physics. You almost certainly know the story of Schrödinger's cat, but the standard telling skips over the part that matters for our discussion. In the original thought experiment, devised by Erwin Schrödinger in 1935, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, the vial breaks, and the cat dies. Quantum mechanics says that before anyone opens the box, the atom is in a superposition of decayed and not decayed states. The puzzle is what this implies for the cat. By straightforward extension, the cat is in a superposition of alive and dead. Open the box, look in, and the superposition collapses to one outcome or the other. The traditional response to this puzzle, the one taught in most introductory physics courses, is what is called the Copenhagen interpretation. On the Copenhagen view, the act of measurement is special. Before measurement, the quantum system has a wave function that includes all possible outcomes. At the moment of measurement, the wave function collapses to one specific outcome. Why this happens, what counts as a measurement, where the boundary between quantum and classical lies, these are not answered by the theory. They are simply postulated to work. For decades, most working physicists were content to use the Copenhagen interpretation as a computational tool without worrying too much about its philosophical foundations. The mathematics works, the predictions match experiment, and asking deeper questions was considered unproductive. In 1957, a graduate student at Princeton named Hugh Everett produced a doctoral thesis that suggested a different way of thinking about it. Everett asked, what if the wave function does not collapse? What if it is exactly what the equations say it is? A real physical object that evolves smoothly according to the Schrödinger equation, with no special role for measurement at all. If you take this seriously, you get something startling. When a measurement is made, the wave function of the entire system, including the observer making the measurement, evolves into a superposition. One component of the superposition has the cat alive and the observer seeing a live cat. The other component has the cat dead and the observer seeing a dead cat. Both components are equally real. They simply describe different parts of the same wave function. From the perspective of either observer, the universe appears to have made a definite choice, but globally, no choice was made. Both branches continue to exist. This is the many worlds interpretation, sometimes called the Everettian interpretation, or the relative state formulation. For decades after Everett published it, it was considered a fringe idea. It seemed to multiply universes wildly. It seemed wasteful. It seemed to require taking the mathematics too literally. Most physicists preferred Copenhagen, even with its conceptual gaps, because at least Copenhagen left them with one world. Over the last several decades, the many worlds interpretation has steadily gained professional acceptance. By 2026, it is one of the 3 or 4 leading interpretations of quantum mechanics. Alongside Copenhagen, the various hidden variable theories like Bohmian mechanics, and the more recent cubist and relational interpretations. It is taken particularly seriously in cosmology, where the notion of an external observer making measurements on the universe as a whole is incoherent, and in quantum information science, where the structure of branching turns out to map cleanly onto the structure of quantum computation. Let me address one common misunderstanding before going further, because it trips up almost everyone. Many worlds is often described as if it creates new universes every time a measurement happens, doubling or tripling reality with each quantum event. This is not what the theory says, and it is not what its defenders believe. The wave function was always there. Its total amplitude is conserved. Branching is just the process by which the components of an already existing wave function become effectively isolated from each other. No new energy is being created. No new matter is being created. One single wave function is doing what wave functions do, and what we perceive as the appearance of new branches is just the inability of decoherent components to influence each other anymore. The mechanism by which branches become effectively isolated is called decoherence, and it is one of the more important developments in quantum theory of the last 40 years. When a quantum system interacts with its environment, the components of the system that correspond to different outcomes become entangled with different states of the environment. Once that entanglement spreads to enough environmental degrees of freedom, the components can no longer interfere with each other in any practical way. They are, For all observational purposes, separate worlds. Decoherence does not require any special collapse. It happens naturally, in extremely short timescales, whenever a quantum system interacts with the macroscopic world. Sean Carroll, who is among the most prominent contemporary defenders of many worlds, has argued that the theory is actually the most parsimonious interpretation of quantum mechanics, not the most extravagant. The reasoning goes like this. Every other interpretation adds something to the bare mathematics of quantum theory. Copenhagen adds a postulate of collapse. Bohmian mechanics adds hidden variables. Cubism adds a subjective interpretation of probability. Many worlds adds nothing. It simply takes the wave function at face value and follows it where it leads. The branches are not extra ontology. They are what the wave function looks like when you stop pretending it collapses. That argument convinces some physicists and not others. The objections are real. One is the preferred basis problem. The wave function can be decomposed into branches in many different mathematical ways, and the theory does not, by itself, tell you which decomposition corresponds to physical reality. Decoherence helps, but the technical details are subtle. Another objection is the derivation of the Born rule. The Born rule says that the probability of an outcome is proportional to the squared amplitude of the corresponding branch. In Copenhagen, this is postulated. In many worlds, ideally, it should be derivable. There are several attempted derivations, none entirely uncontroversial. A third objection is purely aesthetic. Many people simply find the proliferation of branches distasteful, regardless of whether it is parsimonious in any technical sense. There is a recent and interesting paper from 2025 in the Philsy archive examining the structure of branching with care. The result is that branching, properly understood, is genuinely non-local for entangled systems. The branches do not split independently in each spatial region. They split globally, all at once, across the entire entangled system. This is not new physics. It is a clarification of how to think about what many worlds actually claims. It also strengthens the argument that many worlds is most natural when applied to the universe as a whole, rather than to local systems. What about the number of branches? This is one of the questions where physicists have to be careful with their language. If you tried to count branches at a rate of 1 branch per quantum event, the rate would be somewhere in the range of 10 to the 80th to 10 to the 100th per second per cubic meter, depending on what you counted as an event. But this number is essentially heuristic. There is no agreed quantum mechanical procedure for assigning a specific count to branchings, because the branching itself is a feature of the decomposition of the wave function, not a physical event with a definite moment of occurrence. The most honest answer to how many branches there are is that the wave function has a continuous structure, and the number of effectively decohered branches is enormous and growing, but cannot be assigned a specific integer. I want to take a moment to dwell on the implications of level 3 for the way you might think about your own life, because they are unusually direct. If many worlds is correct, then every choice you have ever made, you have also made differently in some branch. Every disaster you avoided, you also suffered in some branch. Every life you could have lived, you are also living in some branch. Every loved one you lost is alive in some branch. Every loved one you have also lost in some other branch. The wave function contains all possible histories of you, weighted by their quantum amplitudes. There is no way to communicate with the other branches. Decoherence prevents it. Once 2 branches have separated, their interference is, for all practical purposes, vanishingly small. You cannot reach across the wave function to the version of yourself that took the other path. You can only experience your own branch, and your branch is uniquely yours. That, I think, is the calming reframe. The wave function is enormous and possibly infinite in its branching, but each branch is its own complete world. Your branch is the only one you can ever know. In a sense, you are alone in it, even if there are infinitely many of you spread across the rest. There is a quiet professional culture growing around many worlds, particularly in the quantum computing community. A quantum computer with n qubits is, on the many worlds picture, performing computation across 2 to the n branches simultaneously. The branches are the computational resource. When the algorithm succeeds, it is because the branches have been arranged to interfere constructively at the right output. This is not the official party line in every quantum computing lab, but it is the natural picture for many of the people doing the actual work. The fact that the theory keeps being useful is not an argument that it is true, but it is, I think, an argument that it is taken more seriously than the public conversation suggests. Level 3 is, in my opinion, the strangest of Tegmark's 4. Levels 1 and 2 ask you to accept more universe, just like ours, beyond the horizon. Level 3 asks you to accept that the universe you are in right now is one branch of a constantly branching wave function, and that all the other branches are equally real. It is harder to picture, but it requires less new physics than Level 2, because it falls out of quantum mechanics if you simply refuse to add collapse to the equations. There is one more aspect of Level 3 I want to draw out before we move on, because it changes how the picture feels. Tegmark himself has argued that Level 1 and Level 3 are, in a precise sense, equivalent. The argument goes like this. In Level 1, the other copies of you live elsewhere in physical space. In Level 3, the other copies of you live in other branches of the wave function. But in both cases, the other copies are causally disconnected from yours. In both cases, the other copies share the same probability distribution as the Level 1 ensemble. In both cases, you cannot influence them, and they cannot influence you. From a purely operational perspective, they are the same multiverse, accessed through 2 different mathematical languages. That equivalence, if it holds, is one of the most quietly surprising results in foundational physics. It would mean that the quantum branching we have spent a century arguing about is not really adding anything new to the universe. It is just another way of looking at the same enormous structure that infinite space already provides. The branches you have not lived in this picture are not somewhere else inside the wave function. They are somewhere else inside space. Or rather, they are both at once, because the 2 descriptions are equivalent. Not all physicists accept this equivalence. There are technical arguments about whether the probability measures really do match, about whether locality is preserved in both cases, about whether the Level 1 and Level 3 observers can really be said to have the same kind of existence. But the fact that the question is on the table at all, that 2 of the most discussed multiverse levels might secretly be the same multiverse described twice, suggests that the architecture of the multiverse program is more interconnected than its taxonomy makes it look. If Level 3 takes the multiverse out of space and into the structure of the wave function, Level 4 takes it one more step in the same direction. It takes the multiverse out of physical instantiation entirely. It places it inside mathematics itself. This is the most radical step. Most physicists will not take it. The ones who do believe it might be the most important step of all. Let me show you what they mean. Is less than break time equals 1s is greater than number part 7. Level 4, the mathematical universe. Of all the multiverses we have walked through tonight, the 4th level is the one that physicists are most uncomfortable discussing in public, and the one that, if it is true, would be the most important. It takes everything we have said so far and pushes it one more step. Level 1, extended space. Level 2, extended the values of the physical constants. Level 3, extended the branching of the wave function. Level 4, extends mathematics itself. It says that every consistent mathematical structure is, in some sense, a real universe, not a description of a possible universe. a real one. The multiverse, on this view, is not a collection of possible physical realities. It is the collection of all possible mathematics. The proposal in this form is most strongly associated with Max Tegmark, who has spent decades developing it. Tegmark calls it the mathematical universe hypothesis, sometimes the ultimate ensemble theory. The argument has roots much older than Tegmark, going back through Plato, through Pythagoras, through every philosophical tradition that has ever taken mathematics to be the deepest layer of reality. What Tegmark adds is a specific, modern, physics-flavored form of the claim. He notices that every successful physical theory we have is, when stripped of its philosophical packaging, a mathematical structure. General relativity is a set of equations on a Lorentzian manifold. Quantum mechanics is a set of operators on a Hilbert space. The Standard Model is a particular gauge theory with particular fields. Every theory of fundamental physics, at the end, is mathematics. Tegmark then asks, what is the difference between a mathematical structure that describes a possible universe and a mathematical structure that is a real universe? If our universe is exactly characterized by some mathematical structure, then in what sense is it different from any other consistent mathematical structure? His answer is, there is no difference. Mathematical existence and physical existence are the same thing. Every consistent mathematical structure is a universe. Some of those universes are simple. Some are too simple to contain anything resembling an observer. Some are complex enough to contain stable objects that themselves perform computations and ask questions like the one we are asking now. The universe we live in is one of the complex ones. There are infinitely many other complex ones, with infinitely many other versions of physics, and there are also infinitely many simple ones, with no physics at all in any recognizable sense. The implications are dizzying. Somewhere in the level 4 ensemble, there is a universe described by completely different mathematics than ours, not a universe with different physical constants in the sense of level 2, a universe with different fundamental equations, a universe described by a cellular automaton instead of by partial differential equations, a universe described by a finite group with strange algebraic properties, a universe with no concept of time at all, just a static set of mathematical relationships, a universe in 2 dimensions, a universe in 17 dimensions, a universe in fractal dimensions. Every consistent mathematics, on Tegmark's view, is its own world, and the level 4 ensemble is the union of all of them. What is the appeal of this view, beyond the obvious appeal of its radicalness? The appeal is that it answers a question no other physical theory can answer. The question is, why these laws and not others? Why does the universe have the particular fundamental equations it has, with the particular fields and the particular gauge symmetries? In Tegmark's framework, the question dissolves. There is no privileged set of laws. Every consistent set of laws is realized somewhere. The mathematics our universe happens to use is one mathematics among all possible ones. It has no special status. The fact that we observe these particular laws is just because we live in this particular structure. Other observers, in other structures, see other laws. The question why these and not those becomes the question why this seat and not the next one over. The appeal also extends to what is sometimes called the unreasonable effectiveness of mathematics in physics. This is a phrase from the physicist Eugene Wigner, who in 1960 wrote an essay marveling at the way mathematical concepts developed for purely abstract reasons keep turning out to describe the physical world with extraordinary precision. Complex numbers, invented for solving algebraic equations, turned out to be essential for quantum mechanics. Group theory, developed for studying symmetry, turned out to govern the structure of fundamental particles. Riemannian geometry, invented for purely geometric reasons, turned out to be the language of general relativity. Why does this happen? Wigner asked. The mathematical universe hypothesis offers an answer. It happens because the universe is mathematics. The reason mathematics works in physics is that physics is mathematics all the way down. Now, the objections are also strong and worth taking seriously. The first objection is that most mathematical structures are not the kind of thing that can contain observers. A static set of relationships, with no temporal evolution, with no concept of change, cannot contain a sequence of mental states. So most level 4 universes, by this argument, are not really universes in any meaningful sense. They are just abstract structures sitting there in the Platonic background with no one in them. Tegmark's response is that the structures complex enough to contain observers are themselves mathematical patterns, and we are one such pattern. We do not need to be made of stuff. We need only to be mathematics that has the right kind of internal structure to constitute an observer. The second objection is what philosophers call the problem of vacuity. A theory that says every possible thing is real does not really tell you anything about your particular situation. It does not predict anything. It does not constrain anything. It just gives you a maximally generous metaphysics. Many physicists find this unsatisfying because they want a theory to make distinctions, to say one thing is more likely than another, to make predictions that could, in principle, be falsified. The mathematical universe hypothesis does none of this. It says everything possible exists, and you are in one of the parts where you can exist. The third objection is that it requires taking mathematics to be a fundamental layer of reality, rather than a tool that human minds use to describe physical things. This is a philosophical commitment, often called mathematical realism or mathematical Platonism, and it is genuinely contested in philosophy of mathematics. Many philosophers hold that mathematics is not a thing that exists independently of human minds. It is a system of symbols and rules that we use very effectively to model the world. On the anti-realist view, the mathematical universe hypothesis is asserting the reality of something that is just a useful fiction. The argument over this point has been going on for 2,000 years and is not going to be settled here. What I find most interesting about level 4 is the way it interacts with the simulation hypothesis, which we will discuss in more detail in a later part. If you accept level 4, then the simulation hypothesis becomes almost trivially true. Every possible simulated universe corresponds to a mathematical structure, namely the structure of the computation that produces it. So every simulation that could be run is already realized in the level 4 ensemble. There is no extra work for an actual simulator to do. The simulated universes exist, regardless of whether anyone is running them. The simulator just becomes one possible cause among many for those universes to be instantiated. And on Tegmark's view, the instantiation is not even needed. Mathematical existence suffices. You can see why most working physicists do not engage with level 4 publicly. It is hard to publish papers in journals about a claim that has no predictive content, that postulates infinite extra structure, and that requires philosophical commitments most physicists prefer not to take a stance on. There is no experiment that could distinguish a level 4 universe from a non-level 4 universe with the same physics. The hypothesis is, in the strictest sense, beyond the reach of empirical science. Whether that makes it metaphysics, or whether it makes it the most important physical insight ever proposed, depends on which side of the falsifiability question you stand on. Tegmark's own defense is that level 4 is the only way to fully resolve the question of why these laws and not others. As long as you accept that there are fundamental physical laws of any kind, you are implicitly accepting that some laws are real and others are not, and you have no principled way to say why. Level 4 removes the asymmetry. Every consistent set of laws is real. The asymmetry between our laws and others becomes a feature of our particular position within the larger ensemble, not a fact about reality itself. I want to mention one more thing before we leave level 4, because it is, in a sense, the most haunting implication. If level 4 is correct, then the question, what makes our universe special, has no answer. There is nothing special about it. It is one mathematical structure among all consistent ones. The patterns we recognize as physical laws are not laws in any fundamental sense. They are just the features of the particular mathematics we are made of. Other patterns in other mathematics are equally real, equally fundamental, equally the home of their own observers, asking their own questions. We are not in any privileged position. We are one corner of a much, much larger structure that contains everything that could ever be. Let me try to make level 4 feel less abstract, because the abstractness is part of what makes most people slide off it. Consider an extremely simple universe. It contains, let us say, 3 objects that we will call alpha, beta, and gamma. Their behavior is governed by a single rule. Every second, each object swaps positions with the next one in a cyclic pattern. That is the entire universe. It has objects. It has dynamics. It has time. It is internally consistent. It does not have observers, but it does not need them in order to exist as a mathematical structure. On Tegmark's view, this universe is just as real as ours. It is just much, much simpler. Now, scale up. Consider a universe that consists of a one-dimensional cellular automaton, the kind that Stephen Wolfram has studied for decades. Its behavior is governed by a simple update rule, and it can produce arbitrarily complex patterns. Some of those patterns might, given enough time, contain something resembling computation. Some of those computations might, given enough complexity, contain something resembling observers. The observers, made of cellular automaton patterns, would have their own physics, which would look nothing like ours. They might never realize that they are made of bits in a one-dimensional grid. They might have their own theories of gravity, their own theories of quantum mechanics, their own multiverse proposals. They would be no less real than we are in Tegmark's framework. They are just running on different mathematics. That is what level 4 is asking you to accept. Every consistent mathematical structure, no matter how strange, no matter how unfamiliar its dynamics, no matter how alien its observers, exists. The universe you live in is the small slice you can perceive of an infinity of infinities of mathematical reality, and that infinity contains worlds that no physics you have ever read about would recognize. Tegmark's 4 levels are the most famous and the most widely cited classification of multiverses, but they are not the only one. Other physicists have proposed entirely different kinds of multiverse, ones that do not fit cleanly anywhere in Tegmark's scheme. The most important of these is built not from space, not from branches, not from mathematics, but from time itself. It says that our universe is not unique even temporally, that there have been others before it and will be others after. Let me show you. Is less than break time equals 1s is greater than. Number. Part 8. Cyclic universes, multiverses in time. Every multiverse we have walked through so far has multiplied things horizontally. More space, more bubbles, more branches, more mathematics. The cyclic models do something different. They multiply time. They say that our universe is one phase in an unending sequence, that there was a universe before this one, and there will be a universe after it, and that the chain stretches forever in both directions. The result is a multiverse in time rather than in space, and it produces an answer to how many that is just as enormous as the spatial answers, but with a completely different geometry. 2 main proposals are worth knowing tonight. The first is conformal cyclic cosmology, usually called CCC, proposed by Roger Penrose. He first laid it out in detail in his 2010 book Cycles of Time, and he has been refining it with collaborators ever since. The argument is, in some ways, more elegant than it has any right to be. Penrose starts by asking what the universe looks like in the very far future, after all the stars have burned out, after all the galaxies have dispersed, after all the black holes have evaporated through Hawking radiation, after every massive object has decayed. The far future, taken to its limit, is a universe consisting of nothing but massless particles, photons, and gravitons, spread out across an essentially infinite, empty space. Now, here is where Penrose's argument turns surprising. In a universe with no rest mass anywhere, no clocks are ticking, massless particles do not experience time. There is, in a precise mathematical sense, no scale. The notion of distance loses its meaning because there is no rest mass standard to measure distances against. A universe of pure radiation is, mathematically, conformally invariant. It can be rescaled to any size, infinitely large or infinitely small, without changing any of its physical content. Penrose's move is to identify the conformally rescaled far future of one universe with the hot, dense, radiation-dominated early state of the next universe. The transition from one aeon to the next is geometric. The end of one cycle becomes the beginning of the next, not through any physical event, but through a mathematical re-identification of the conformal structure. Each cycle is called an aeon. The universe is an unending sequence of eons, each one starting from the conformal infinity of the one before. This is a strange idea, and Penrose knows it. The technical challenges are significant. The argument requires that all rest mass eventually decay, which is not yet established. It requires a specific behavior of the gravitational field at the transition, which is mathematically subtle. A 2025 paper, ARXIV 2503.24263, The Physics of Conformal Cyclic Cosmology, introduces what its authors call a gravitational wave epoch as a natural crossover mechanism, smoothing the mathematical transition. The model is still considered fringe by most cosmologists, but it is being developed with increasing seriousness. Penrose and his collaborator Vahe Gurzadian have also claimed observational evidence for the model. They argue that supermassive black holes from the previous aeon, when they collided, would have left fossilized concentric rings in the cosmic microwave background of our aeon. They have published several papers in 2010, 2018, and 2020 claiming to detect these rings in the actual cosmic microwave background data. Most cosmologists are unconvinced. The detected rings are at the edge of statistical significance, and they could be artifacts of the analysis rather than real signals. But the claim is on the table, and it is one of the few cases where a multiverse hypothesis is making testable predictions that have actually been tested. The second cyclic model worth knowing is the ekpyrotic model proposed by Paul Steinhardt and Neil Turok around 2001. Steinhardt, recall, was one of the inventors of cosmic inflation, and his ekpyrotic model is his attempt to build cosmology without inflation, in part because he became dissatisfied with the multiverse implications of eternal inflation. The ekpyrotic model is based on a higher dimensional picture from string theory, in which our four-dimensional universe is a membrane, called a brane, embedded in a higher dimensional bulk. Other branes exist in the bulk too. The model proposes that our universe and a parallel brane collide periodically, and that each collision is a Big Bang. After the collision, the branes separate. The universe expands and cools, structure forms, and eventually, after roughly 1 trillion years, the branes come back together for another collision. In the ekpyrotic picture, our universe is one beat in an eternal drumming. There was no first beat, there will be no last. Each cycle starts hot, cools, forms structure, and ends in another collision. The model has the property that it avoids the unpredictiveness of eternal inflation. It makes specific predictions about the spectrum of primordial gravitational waves, predictions that can, in principle, be tested by future cosmic microwave background polarization experiments. Steinhardt has argued, in a series of papers and public talks, that recent data fits the cyclic model better than it fits the inflationary model. Most cosmologists disagree, but the argument is genuinely alive in the literature. What both of these models share, and what makes them important for our central question, is that they replace spatial branching with temporal succession. Instead of many universes existing in parallel, they propose many universes existing in series. The total number can still be unbounded. If eons have always been happening and will always happen, the number of past and future universes is infinite, but the structure is different. You are not a sibling of those other universes, separated by horizons or by physical constants. You are a descendant, separated by time. There is something philosophically calming about cyclic models, in a way that the other multiverse pictures are not calming. The other levels suggest that you are one instance among many, scattered across an enormous spatial or branching structure. The cyclic models suggest that you are one node in an unending chain. The aeon before this one had its own observers, possibly very different from us, who lived and died and left behind the radiation that became our beginning. The aeon after this one will have its own observers, who will inherit what we leave behind. The universe is not a collection of strangers in different rooms. It is a continuous procession through time. There is also something philosophically difficult about cyclic models. They imply that nothing is final. Heat death is not the end. The eventual evaporation of every black hole is not the end. Whatever happens in our universe, however completely it seems to finish, it is just a prelude to whatever comes next. Some people find that comforting. Others find it exhausting. The honest answer is that the universe does not seem to particularly care which response we have. For our central question, the cyclic models add another candidate to the count. If they are correct, the number of universes is unbounded in time as well as in space. If they coexist with the other multiverse levels, the total architecture becomes even more elaborate. You could have infinite spatial Hubble volumes, in infinite inflationary bubbles, in infinite quantum branches, in infinite cyclic eons, all simultaneously. None of these levels exclude the others. They could all be true at once, multiplying together in ways that no single physicist has fully tried to enumerate. There is a question worth asking about cyclic cosmology that the technical literature rarely confronts head-on. The question is, if there have been infinite past eons, what is the cosmological status of memory? In each aeon, complex structures arose. Observers asked questions. Civilizations may have built up enormous amounts of understanding about their own universe. Then the aeon ended. The black holes evaporated. The radiation diluted. The information that had been collected about that aeon was, on the standard picture, lost. In Penrose's framework, the only thing that crosses from one aeon to the next is the gravitational signature of large mergers, and even that signature is faint and contested. So whatever was learned in the previous aeon, by whatever observers existed there, did not survive. It was not handed down. Each aeon, however long it lasts, and however much complexity it generates, ends in a kind of cosmic forgetting. I find that fact strangely affecting. The cyclic models do not give us continuity in any meaningful sense. They give us repetition without inheritance. There is, on this picture, no accumulation across aeons. Each cycle starts from the same kind of beginning and ends in the same kind of forgetting. Whatever joy or grief or discovery filled the previous aeon, none of it crosses the boundary. The universe gets to start clean every time. Whether that is a relief or a tragedy is a question the physics cannot answer. To bring it back to the central thread, cyclic cosmology is yet another candidate that the word multiverse hides. It is a multiverse in time rather than in space, and some physicists, including one of the inventors of inflation, believe it is the real answer that the inflationary multiverse has been masking. Whether or not they are right, the existence of the cyclic alternative shows just how much room there is for completely different conceptions of what other universes might be. Tegmark's 4 levels and the cyclic models together still do not exhaust the territory. Other physicists have proposed completely different multiverses, and one published taxonomy lists 9 of them, of which Tegmark's 4 are only a part. Let me run through what those others look like. Is less than break time equals 1s is greater than number, part 9. Brian Greene's 9 brains, holograms, simulations. Tegmark gave us 4 levels. In his 2011 book, The Hidden Reality, the Columbia University physicist Brian Greene catalogued 9. The overlap with Tegmark is significant. Greene's quilted multiverse is essentially the level 1 of infinite Hubble volumes. His inflationary multiverse is the level 2 bubbles. His quantum multiverse is the level 3 branching of the wave function. His ultimate multiverse is the level 4 mathematical ensemble. His cyclic multiverse is the temporal succession we just discussed. So far, that is 5, and they overlap cleanly with what we have already covered. Greene then adds 4 more that do not fit anywhere in Tegmark's scheme. They are worth touring briefly because they represent the genuine range of multiverse proposals in modern physics. The first is the brain multiverse, which we touched on through the ekpyrotic model in the last part. The brain picture comes from string theory, which requires more than 4 dimensions of space-time to be mathematically consistent. The extra dimensions are usually assumed to be curled up very small, but in brain scenarios, some of them can be large, and our universe can be a 4-dimensional surface, called a brain, embedded in a higher dimensional bulk. Other brains can exist in the same bulk, with their own observers, their own physics, their own histories. These other brains are not infinitely far away in our familiar dimensions. They are very close in some of the extra dimensions, but they are inaccessible because matter is bound to its own brain. Only gravity, which spreads through the bulk, can interact between brains. The famous Randall-Sundrum models of the late 1990s developed this picture in mathematical detail. The second is the holographic multiverse, based on the discovery that certain theories of gravity in a region of space-time are mathematically equivalent to certain non-gravitational theories on the boundary of that region. This is called the ADS, CFT correspondence, and it was first proposed by Juan Maldacena in 1997. The idea is that the bulk and the boundary are 2 equivalent descriptions of the same physics. They are not 2 separate universes. They are one physics described in 2 ways. But the question this raises is which description is fundamental. If the bulk and the boundary are equivalent, which one is the real universe and which one is the derived description? Greene catalogues this as a multiverse because, on some readings, both descriptions are equally real, making each region of space-time, in some sense, double. The third edition is the family of string theory vacua treated as a multiverse in its own right. We already discussed this as the mechanism that populates level 2, but Greene treats it as a separate category because the family of vacua exists, in some sense, as a mathematical object independent of any specific cosmological scenario that populates it. Every stable string theory solution corresponds to a possible universe with its own physics, and the collection of all stable solutions is, in itself, a kind of multiverse. The fourth edition is the simulated multiverse. This is the proposal that our universe is one of many simulations being run on some larger substrate, that the substrate may itself be running many such simulations, and that the total number of simulated universes vastly outnumbers any base reality universes. We are going to give this one its own part next, because it has its own argument structure and it has bled most aggressively from physics into popular culture, so it deserves a more careful treatment. What Green's catalogue makes clear, taken alongside Tegmark's, is that there is no single answer to what a multiverse is. Different physicists carve the territory differently. Some include all of these proposals. Some include none. Some treat brain multiverses as a subspecies of level 2. Some treat the holographic correspondence as a curiosity rather than a multiverse. Some treat string theory vacua as a separate ontological commitment. Some collapse the whole question into the simpler observation that infinite space contains repetition and stop there. To bring it back to the central thread, the more carefully you count, the larger the answer to the question how many becomes, and the clearer it becomes that multiverse is a family of related ideas rather than a single one. The word is doing a lot of work. The next part is going to look at one specific candidate that has wandered far from physics into something stranger and is now part of how a lot of people think about reality, even though most physicists do not actually take it as a physics claim. Let me show you the simulation argument in its cleanest form. Is less than break time equals 1s? Is greater than number. Part 10. The simulation argument. The simulation hypothesis is, in its modern form, the work of the philosopher Nick Bostrom, who published his trilemma in a 2003 paper called Are You Living in a Computer Simulation? The argument has since escaped from academic philosophy into mainstream culture, helped along by movies, books, and tech industry enthusiasts. It is worth understanding in its clean form, because most public versions of it are sloppy. In its clean form, the argument is more interesting and also more limited than the popular version. Bostrom's argument has a specific structure. He proposes that at least one of 3 statements must be true. The first is that civilizations capable of running ancestor simulations almost always go extinct before they reach that level of capability. The second is that civilizations capable of running ancestor simulations almost always choose not to run them. The third is that the number of simulated observers vastly outnumbers the number of base reality observers, and therefore, by the principle of indifference, you should expect to be a simulated observer. Notice what Bostrom does not say. He does not say we are in a simulation. He says either civilizations go extinct, or civilizations stop simulating, or we are probably in a simulation. The argument is a trilemma, and its only conclusion is that one of those 3 options is correct. Which one is correct, the argument cannot say. To get from the trilemma to the conclusion that we are simulated, you have to add the assumption that the first 2 options are unlikely, that civilizations do not generally go extinct, and that capable civilizations do generally run many simulations. Both of those are contentious. The mathematical core of the argument is the observation that if a civilization reaches sufficient computational power, it can run an enormous number of simulations of its own history, possibly trillions, possibly more. Each simulation contains simulated observers. If you sum up all the simulated observers across all the simulations, across all the simulating civilizations across the history of the universe, the total will dwarf the number of base reality observers by a factor that could be many orders of magnitude. So if you are picked at random from the set of observers, you are overwhelmingly likely to be a simulated one. This is the indifference reasoning, and it is the engine of the argument. There is an interesting connection between the simulation hypothesis and Tegmark's level 4. Every simulated universe is, formally, a computation. Every computation corresponds to a mathematical structure. Every mathematical structure in Tegmark's framework is already a universe, so the simulated universes are not extra ontology beyond level 4, they are subsets of it. The simulators, on this view, are not creating new universes by running simulations. They are just instantiating mathematical structures that, on Tegmark's reading, exist whether they are instantiated or not. This collapses the simulation question into a special case of the broader mathematical universe question. There is also a substantial literature on the physical constraints on the simulation hypothesis. A 2022 paper on the RZEV Constraints, Observations and Experiments on the simulation hypothesis surveys what we could in principle learn about whether we are in a simulation. The general conclusion is mostly negative. Any simulation indistinguishable from base reality is, by definition, indistinguishable. The hypothesis is, in the strictest sense, unfalsifiable. There are some proposed signatures, such as discreteness in the cosmic ray spectrum at very high energies, but none of them have produced any evidence so far, and most of them would be consistent with non-simulation physics anyway. There is also the question of nested simulations. If we are in a simulation, then the simulators may themselves be in a simulation. There is no principled limit to how far down the stack might go. The hypothesis can be extended indefinitely, with each layer containing the layers above it. Whether this is mathematically coherent depends on whether infinite computational regress is allowed, which is itself contested. I bring up the simulation hypothesis tonight, in the context of counting multiverses, because it functions as another candidate that the word hides. It is not a parallel universes claim in the spatial sense. It is not a quantum branching claim. It is a question about whether our universe is fundamental or whether it is one layer of a deeper computational stack. Some physicists treat it seriously as a multiverse candidate. Most do not, because it slips so easily into bad metaphysics, but they do not have a principled argument for excluding it, beyond the general feeling that it is a category mistake to count simulations as universes alongside cosmological multiverses. To bring it back to the central thread, the simulation hypothesis is best understood as one more proposal that the word multiverse can refer to, and it shows just how flexible the word has become. It is not a physics claim in the same sense as eternal inflation or many worlds. It is a metaphysical claim with mathematical scaffolding. Including it in the count is a judgment call. Excluding it requires drawing a line between metaphysics and physics that, as we are about to see, is itself genuinely contested among physicists. The deeper question is whether any of this counts as science at all. That is the question we have to face before we can finalize our count. Is less than break time equals 1s, is greater than number part 11, the skeptic's case. Every multiverse we have walked through tonight shares one feature. None of them can be directly observed. Level 1 is past the cosmic horizon. Level 2 is in other bubbles we cannot reach. Level 3 is in branches that have decohered from ours and cannot interfere with our world. Level 4 is in mathematics we are not made of. The cyclic eons are in a temporal past and future causally disconnected from us. The brain universes are bound to their own membranes. The simulation, if it exists, is by construction indistinguishable from base reality. The whole architecture is, at the level of direct observation, completely invisible. This is the foundation of the skeptic's case, and it is a serious one. We owe it a careful hearing before finalizing our count. The classical criterion for whether something is science, from the philosopher Karl Popper, is falsifiability. A theory is scientific only if it makes predictions that could, in principle, be shown false by observation or experiment. By that criterion, the multiverse, in most of its forms, is in trouble. If the other universes are by construction inaccessible, the theory cannot be falsified by anything we observe in our universe. Other things we infer about, like distant galaxies or the early hot dense state, we infer through chains of evidence that include observable consequences. With the multiverse, the chain often runs out before reaching anything we can actually check. The most vocal skeptic among working physicists has been Paul Steinhardt, who, as I mentioned earlier, was one of the inventors of cosmic inflation in the 1980s. Steinhardt's argument is precise and worth quoting. He notes that inflation, in most reasonable versions, becomes eternal. Eternal inflation produces an infinite number of pocket universes with every possible value of every physical constant. So the theory predicts that any constant we measure can take any value. It predicts no specific value for any constant. It therefore makes no specific predictions about our universe. A theory that predicts everything, Steinhardt argues, predicts nothing. He has spent the last decade or more arguing that inflation in its modern multiverse form is not really science, and that cyclic cosmology, whatever its other limitations, at least makes specific predictions that can be checked. Steinhardt's defection from his own creation is significant. He is not an outsider attacking from the sidelines. He is one of the people who built the theory, watched it become orthodoxy, and concluded that it had gone wrong somewhere. Other inflation pioneers, including Alan Guth and André Linde, disagree with him and argue that the inflationary multiverse is still doing important explanatory work. The argument among them is ongoing. Sabine Hossenfelder has been even more direct. She has argued in essays, talks, and her popular book, Lost in Math, that the multiverse is, in her phrase, no better than God. Both, she argues, are unfalsifiable metaphysical postulates that explain everything by accommodating any possible observation. Both are appealing for aesthetic reasons rather than empirical ones. Both are, in her language, ascientific, not wrong, but not science either. Her position is that physics has lost its way by pursuing ideas that cannot be tested, and that the multiverse is one of the most flagrant examples. George Ellis and Joe Silk, two highly respected cosmologists, published a 2014 commentary in the journal Nature, calling on the physics community to defend the integrity of the falsifiability criterion against what they saw as encroachment from untestable ideas like the multiverse and string theory. Their argument was less personal than Hossenfelder's and more institutional. They were worried about the long-term health of physics as a science. They wanted the field to draw a clearer line between what is testable and what is metaphysics. There is a specific technical problem that critics like to point to as a symptom of something gone wrong, and it is called the Boltzmann brain problem. In an eternally inflating multiverse, or in any multiverse with an unbounded amount of space-time, ordinary observers like us are not the only kind of observer that can arise. In an enormous eternal sea of quantum and thermal fluctuations, brains can spontaneously fluctuate into existence, complete with false memories and the conviction of being normal observers. These are called Boltzmann brains, after the physicist Ludwig Boltzmann, who first considered something like them in the late 19th century. In an eternal multiverse, Boltzmann brains might vastly outnumber ordinary observers like us. If they do, then any given observer should expect to be a Boltzmann brain. We are not Boltzmann brains. So, either the theory predicts something obviously false, or there is some way to suppress the Boltzmann brain prediction that we have not yet found. The fact that this problem persists is, for many critics, evidence that the multiverse predictions are not as well defined as their defenders claim. Then there are the swampland conjectures, developed in recent years by Qumran Vafa and his collaborators. The conjectures argue that most of the apparent vacua of string theory may not actually correspond to consistent quantum theories of gravity when you account for all the constraints. The effective number of allowed vacua could be far smaller than the famous 10 to the 500th estimate, possibly even 0. If the swampland conjectures hold up, the string theory contribution to the multiverse shrinks dramatically, which would significantly weaken the case for level 2 as currently understood. This is an active area of research, and the outcome matters for the multiverse count. The defenders of the multiverse program have responses. They argue that indirect evidence still counts, even if direct observation is impossible. The cosmological constant problem is real. The fine-tuning of various constants for the possibility of complex chemistry in observers is, on the standard analysis, extreme. The multiverse, in some form, is the simplest naturalistic explanation for these facts. To reject it requires either accepting brute facts about the constants without explanation or proposing some other mechanism that has not yet been found. Most defenders are willing to live with the unfalsifiability cost in exchange for the explanatory benefit. Sean Carroll has staked out a middle position that is worth flagging because it cuts the question along an interesting line. He argues that level 3, the many worlds interpretation, is on completely different epistemic footing than the other levels. Many worlds is not an extra postulate added to quantum mechanics. It is what you get when you take quantum mechanics seriously without adding a collapse postulate. So the standard unfalsifiability objection misfires against many worlds in particular. If you accept the empirical content of quantum mechanics, the other branches come with it whether you like them or not. You are not adding to physics by accepting them. You are just refusing to add a collapse postulate to remove them. Whether or not you find this argument persuasive, it has the merit of distinguishing between different multiverse proposals on epistemic grounds. Some of them, like many worlds, follow directly from already accepted physics. Others, like level 4, require taking on substantial new metaphysical commitments. A blanket dismissal of all of them as unfalsifiable elides this difference. The honest summary is that the multiverse program lives in an uncomfortable zone between physics and metaphysics. Some parts of it might be testable in principle, through bubble collision signatures in the cosmic microwave background, through branching effects in quantum computers, through ring patterns in conformal cyclic cosmology, through other indirect signatures that have been proposed. Most of it is not testable, even in principle. The field is genuinely divided on whether this matters. Some physicists believe the explanatory power justifies the cost. Others believe that physics, by abandoning falsifiability, has wandered out of science altogether. To bring it back to the central thread, the answer to how many multiverses are out there depends not only on which physical theories you take seriously, but on what you count as a scientific claim in the first place. There is no neutral answer to that second question. It is itself contested. So the count we are about to attempt in the final part is going to come with caveats. It is going to be a count of possibilities, not a count of established facts. With all of that on the table, let us try to add it all up. Is less than break time equals 1s is greater than number part 12. How many? Then we have laid out the architecture. We have walked through the 4 Tegmark levels, the cyclic alternatives, the additional green proposals, the simulation argument, and the skeptic's case against the whole program. We are finally in a position to attempt the count. The answer is not going to be a single number. That is part of the honesty of the exercise. If level 1 is correct, and space is genuinely infinite, with roughly the same physics everywhere, then the count is unbounded. Infinite Hubble volumes, infinite copies of every possible arrangement of matter, infinite copies of you, infinite copies of this video, playing on infinite screens at this exact moment. The infinity is the simplest infinity in physics. It is countable in the sense that you can tile infinite space with discrete Hubble volumes and put them in a sequence. If level 2 is correct, and eternal inflation produces bubbles with different physical constants, then the count is an infinity of infinities. Each bubble universe has its own level 1 infinity inside it. The total is some hierarchical infinity whose precise cardinality depends on the structure of the inflating background. The number is too large for any meaningful operations to be performed on it. If level 3 is correct, and the wave function never collapses, then the count is an uncountable continuum of branching states, multiplying continuously through time. The number per second is not even well defined, because the branching is a feature of the decomposition of the wave function rather than a discrete event with a definite count. The total is, in some sense, every consistent quantum history of the universe. If level 4 is correct, and mathematical realism applies, then the count is the cardinality of all consistent mathematical structures, which is an even larger infinity than the previous ones, and which contains all of them as special cases. If the cyclic models are correct, in addition to or instead of the spatial multiverses, then the count is multiplied by the temporal axis. Infinite past eons, infinite future ones. Each aeon could itself contain its own Hubble volumes and inflationary bubbles. The stack becomes higher. If the simulation hypothesis is correct, the count is multiplied by however many layers of simulation exist. If the stack is finite, the count is finite. If it is infinite, the count is unbounded. If you stack all of these together, the count is undefined. The total is some product of infinities of different cardinalities, with no agreed mathematical framework for combining them. The honest answer to how many is that there is no honest answer, only a layered architecture of possibilities, each of which has its own count, and yet none of this is verified. Every layer might be wrong. The cosmological constant might turn out to have a deeper explanation we have not found, removing the strongest empirical pressure for any multiverse at all. Inflation might not actually be eternal in nature. Many worlds might be a misreading of quantum mechanics. Mathematical realism might be a category error. Cyclic cosmology might not survive close observational tests. The simulation hypothesis might be empty. This is the strange place we arrive at when we count carefully. The most extraordinary possibility on this analysis is not infinity. It is the number one. To believe that ours is the only universe, given everything we have laid out, requires extraordinary evidence against everything else, evidence we do not currently possess. The multiverse, in some form, is the default position you arrive at by following the implications of theories we already accept. To reject all of it is, in a sense, the radical move. We do not know how many. We may never know. The other levels might be permanently beyond verification. The question itself might turn out to be malformed, in some way we cannot yet see. But the question, asked precisely, is one of the most beautiful questions physics has ever produced. The universe has been generous with its mysteries, and this is one of the largest of them. What I hope you carry away from tonight is not a number. It is a sense of the shape of the question. The word multiverse, you have learned, hides at least 4 logically independent ideas, and possibly 9, depending on how you count, and possibly more if you include the temporal and the simulated and the holographic. Each of these ideas rests on different physics. Each predicts a different answer to the question how many. Each is independently disputed by serious physicists who know the math better than either of us. There is no single multiverse story. There is a family of related questions with a family of related answers, and the honest position is to hold them all open, weighing the evidence as it comes in over the next decades and centuries. There is something quietly reassuring about that openness, I think. It means physics is still in the middle of the story. It means there are still discoveries to be made that could change the answer. It means the universe has not yet given us its final number, and we are still in the part of the conversation where everything is possible. That is the kind of unfinished question worth falling asleep to. If even one of the levels we have discussed tonight is real, then somewhere out there, beyond every horizon physics has ever drawn, there is another you, listening to another voice, asking the same question, and you will never meet, and the loneliness of that fact and the wonder of it are the same fact, seen from 2 sides.